Hello, it's Andy here, and welcome back to my walkthrough of the 2019 Sans Holiday Hack. So far during our time here at the North Pole, we've uncovered a threatening ransom note, a series of attacks on Elf University computer systems, and an evil plot by an unknown attacker to destroy Christmas by interfering with Santa's sleigh. At the end of the last episode, we were provided with an encrypted document which is somehow related, but before we get to decrypting it, let's go give Holly a visit to help with the terminal challenge. We're tasked with finding a quiz solution from a Mongo database. Mongo is quite different from a more traditional database in that it is non-relational and document-orientated. It and other NoSQL databases can provide a better solution for big data applications where the data doesn't always fit a particular rigid structure or format. We'll start by running the Mongo client app. But we get an error about not being able to connect. PS tells us the Mongo server is running, but it's been told to start on a non-standard port, so we need to pass this to our client app. Once connected, we can list databases using showDBs. Of the databases listed, ElfU is probably a good place to start. We list the collections within that database using showCollections. Again, one item jumps out here, solution. We can list the contents using the find command. It's a message telling us to run a display solution script. Could it be this easy? Yeah, we see a notification that we've solved this terminal. Back to the main objective. Krampus has provided us with an encrypted document which we need to decrypt, but we don't have the decryption key. He does, however, provide the program used to encrypt and decrypt files at the North Pole, plus its debug symbols. We're also told that the file was encrypted between 7 PM and 9 PM on the 6th of December 2019. Without the decryption key, we're faced with having to try and brute force our way to the unencrypted document, unless we can identify and exploit a bug or error in the encryption software or key management system. Ron Bow's talk at this year's KringleCon has some great tips to help reverse engineer the encryption software, and the debug symbols provided by Krampus should make this job a lot easier. We'll start by opening the Elf encryption program in IDA. Note how many of the subroutines listed on the left do not have a useful or friendly name. Like this, we'd have to manually analyze each to understand its function, but loading the debug symbols tells us the names given to these functions by the original developers. Now it's much easier to see what each does, so we can take a browse through subroutines which have interesting names. Main is the initial entry point. This looks like a menu system, and makes calls to do encrypt and do de-encrypt. Do encrypt is clearly the encryption routine, which generates a new key each time it's run via the generate key function. It encrypts using des in CBC mode, and after encrypting the file, a store key function is called. It's worth noting here that des is a symmetric algorithm, meaning that the same key is used for decryption as is used for encryption. Generate key, as the name suggests, generates an encryption key based on the super secure srand and random functions. If srand is setting a seed for a random number generator, then it must only be a pseudo-random number generator, and therefore certainly not super secure. There's also a call to time to fetch the current date and time, the output of which is then fed into srand. This looks like it might be the vulnerability we need to crack the encryption. If the current time is used as the seed for the random number generator, we can determine the key if we know when the document was encrypted, which we do. Super secure srand prints the seed to screen and stores it in a variable called state. Super secure random does some maths to state to generate the pseudo-random number and update state for next time. The opcodes here describe arithmetic multiplication and addition, and bitwise shifting and anding. And if we Google some of the constants, we see that the code matches the standard Windows rand function from msvcrt.dll. So, given the seed for each key is set by time, the number of seconds since the Unix epoch on the 1st of Jan 1970, and we know the key was generated in the 2-hour period between 7 PM and 9 PM on the 6th of December, that gives us a possible 7,200 possible keys, based on 60 seconds times 60 minutes times 2 hours. We could probably brute force that many keys, but first let's take a closer look at that store key function we saw earlier. Maybe we can just access the key without needing to resort to brute force. Store key makes a call to the Elfscrow API store function. This returns a secret ID, and if we go back to main, we see that the decryption routine requires this ID. There's an associated retrieve key function too. There may be a weakness in this web service which, if exploited, might give us a list of keys, but we might not be able to reliably identify the precise one used for this document. And besides, we've not been given permission to try and hack the KringleCon system, so let's revert to our pseudo brute force approach. As the encrypted file is a PDF, there's no need to decrypt all of the file in order to determine if the correct key is being used. The encryption key is DES in CBC mode, which works in blocks of 8 bytes, so we just need to decrypt the first 8 bytes and check to see if the first 4 bytes match the magic number for PDF files. All PDF files start with %PDF. It's possible to extract the first 8 bytes of the encrypted document using XXD. Here's some Python code I wrote to replicate the key generation process for each of the timestamp values between 7 PM and 9 PM on 6th of December, and then try decrypting those first 8 bytes with each key. It only takes a few seconds to complete this for all 7,200 combinations. The output can be piped through grep to identify which key results in an output which contains %PDF, represented as 25, 50, 44, 46 in hexadecimal. And we get a single hit. We have found the key. We could use a bit more Python to decrypt the document, but by this time I'd had enough of coding, so just fed the document and key through CyberChef to perform the decryption. The resulting document is the quick start guide for the Super Sledomatic Machine Learning Sleigh Route Finder, the very system that the mysterious Christmas villain had claimed to have found a way to sabotage. For now, we've completed this objective and can submit the answer, but I'll see you in the next episode where we'll finally unmask who's behind the evil plot to destroy Christmas.